Okay, what we're going to try here then is 3-C1, so Unit 3, problem C1. We're going to do problem number 3. This is the Toboggan child. By the way, if you've never owned an actual toboggan, they're amazing. I had one, my uncle got me one from Canada when I was a little kid. It's all wood and everything. We heat wax the bottom. You put about 6 people into the back of that thing. You get moving. I'm just saying, you get moving. Okay? Talk about more of my sledding stories back in class. Okay, so let's read this problem. Problem we got here, and we'll just pop this up on the screen, is that a child is sliding down a hill on a toboggan with an acceleration of 1.5 meters per second squared. If she starts at rest, how far has she traveled in 1 second and then 3 seconds here? Okay, so that's our problem we're doing. What I like to do when I see a problem, oh, I'm going to need that back. I'm going to be able to see that. What I like to do whenever I start a problem is I like to first draw a picture, okay? Your pictures don't have to be good. You're going to see as the year goes on and on, my pictures get worse and worse just because of who I am and I'm not an artist. But here's a picture, okay? So you've got like, I don't know, some hill, and I'm just going to draw a straight line for that. And oh, let's make this child purple. I don't know. No, purple. Green. They're wearing a very 90s neon coat, and then here's the toboggan. Yay! Okay. Snowflakes falling in the background. Okay. So when the kid is at the top of the hill here, they have some initial velocity. And in the problem, it says that she is starting at rest. Anytime you see at rest, you know that it has 0 velocity. So if she's starting at rest, then our initial velocity is 0. Okay? If she comes to a stop or comes to rest, that is a final velocity of 0. But in this case, our initial velocity is 0 here. Okay? In the problem, we also know that for part A at least, she's traveling for 1 second. And in part B, she's traveling for 3 seconds. Okay? We also know, just from given in the problem, that the child's acceleration is 1.5 meters per second squared. And that holds true for both part A and part B. Same with this initial velocity. So we know this initial velocity, once again, is 0. We know the initial velocity, once again, is 0. Okay? Just based on this picture, just based on reading the problem and seeing what we have, I have created 3 things. I have a time, acceleration, velocity. Time, acceleration, velocity. So reading the problem again, if she starts at rest, how far has she traveled in? How far is referencing like a distance or a displacement, okay? You didn't say, oh, how far, you mean 10 seconds? No, how far is a distance, okay, or a displacement. So we're looking for this delta x here. That's what we care about. Now, we did in class the other day the equation picker worksheet, which I gave you 3 unknowns and you were trying to solve for a 4th thing, and that was, we were getting some practice with that. Some of us did well, some of us didn't. This is just that again. You have 3 things, t, a, and vi. You're looking for delta x. Which equation should you pick? I'll give you a second. You want to pause the video? I don't want to pause the video. I just want to keep going. If I think about this, well, I'm looking for delta x. It exists in equations 4 and 5 have delta x in it. It also exists in equation 6, but equation 6 doesn't have time, so I can't use equation 6. I'm stuck with either 4 or 5. Equation 4 on our best friend has a final velocity. Equation 5 doesn't have a final velocity, so I can use it. I can say that delta x equals vt plus 1/2 at squared. And if that means nothing to you, then you need to check out a very specific video, which we can only see in class due to copyright infringements. Ugh. Anyways, we see we've got this equation here. It applies to both parts A and B, so we just have to shove in values. We can just say here that delta x equals our initial velocity, and I like putting all these in parentheses just so I know to keep them all apart. The initial velocity is 0 times a time. Well, 0 times 1, I didn't even need to write that, did I? I could have just said 1/2 of 1.5 times 1 squared. Well, 1 squared is just 1, and then 1/2 of 1.5 is just 0.75. Distance or displacement comes out to be meters. We can also see it comes out to be meters because what we have here is meters per second squared times 1 second squared. Our second squareds divide out. Okay, and there was nothing here because they all canceled out. But if there was, it'd be meters per second times second, and we get meters again. So that's part A right there. For part B, we're doing the same thing. Delta x equals 0 again times time. I don't care. It's just going to go away. Plus 1/2 1.5 times 3 squared. 3 squared is 9. 1.5 times 9 is, let's see, 9 plus 4.5, 13.5. And then whatever 13.5 is divided by 2, I think that's going to be 6.75 meters. If I'm correct, because 6 doubled is 12, and that's 1.5, so yeah. Whoops. There we go. Those are our answers. Okay? Wasn't really too worried about sig figs. It's not what this is about right here. We're trying to learn how to look at these type of problems. Okay? Once again, big thing I did is I started off with this loving picture. Okay? Pictures first. That picture and reading the problem allowed me to understand what variables I had. It allowed me to understand what variables I was looking for. And then it was just a matter of busting out the best friend and choosing the right equation. Once we did that, we're set. Okay? So that's how we do 3-C1. Problem number 3, the toboggan child. There are answers. Fin. We're done here. Ninja Kyle, how are we able to watch the video at home? I'm assuming you're talking about the